Thank you. So, let's try. Okay, so hello everyone. This is my first lectures with you. I will give 3 of them, and Véronique Buat, also from Marseille, will give a couple others which have been planned together in the sense that we try to not overlap too much and present you some basic elements, basic physics of galaxies and on the evolution and about how you can measure some properties of galaxies. So I will give you these 3 lectures, and Véronique will give 2 more, which are more about how to measure star formation rates, stellar masses, and analyze the light that we get from galaxies. In this first one, I will talk about chemical evolution. It's also a way to introduce many concepts which are important for galactic physics. And of course, it is a school about cosmology, but galaxies are the bricks of the universe in a sense, and they are what you can see, and usually you use galaxies to study also cosmology. So it's good to know a bit of important concepts about that beyond being interested in the evolution itself of galaxies. So I'm going to start by a very, very generic introduction about chemical evolution at a very basic level, and then we will go further. So you already have seen this image a couple of times, maybe a bit more. This is a Planck image of the cosmological background, and this is one of the main proofs that the universe has now a very uniform, homogeneous, dense period. And if we extrapolate with cosmological models, it means that the universe has evolved from a very hot, dense, uniform state. And when people do computation of theoretical physics and nuclear physics in this scenario, in this concept, they can compute the temperature evolution of the universe. And they can compute what are the nuclear reactions which are possible in these temperatures. So in the early phase of the universe, the reactions that were possible are schematized here. And basically what it means is that the Mendeleev table of the primordial universe was much shorter and very easy to remember. You had hydrogen, helium, a bit of lithium. And this is a representation where the surface is proportional to the abundance of the different elements. So of course you see 75% of hydrogen and 25% of helium and some traces of light elements. So of course the situation today is much different. So if we keep this primordial thing in the corner here, and now this is a similar representation for the abundances at the surface of the Earth. So that's very easy to do, right? And as you know, on Earth, well, there is still some hydrogen, of course, but there is oxygen and carbon, which is good for us. There is a lot of iron and a lot of other elements. So the situation has drastically changed from this point of view. Of course, this is the Earth, and the abundance at the Earth's surface has also been affected by the formation of the solar systems and the planets. So the situation is a bit different if you look to a more global perspective, but we can do that because we can measure by spectroscopy abundances in stars, in the sun, for instance, or we can measure in a primordial object in the solar systems. And so we can have an idea of the current today, typical abundance of different elements in the universe. And this is a table showing you that the abundance of the elements as a function of the number of nucleons in the nucleus of atoms. So in this case, you see that hydrogen and helium are still dominant today, but you see there is a range of elements like carbon, oxygen, like on Earth, which are relatively abundant, peak of elements around the iron, and a lot of other elements, basically all the table, with various effects that can be seen here, and I will not go in details of all of them.
But it's a bit misleading. Lithium is very important for nucleogenesis. Right, but the
abundance is very low, but it's an important element.
They should know that is.
Of course. So maybe during the question you can come back to the lithium because I will not speak much about it actually. It's a special case in a sense. Okay, and today universe is also composed of many galaxies, billions of galaxies in the observable universe, and in these galaxies you see all these elements. So the transformation from the uniform universe with just hydrogen and helium and what we see today in abundances and in galaxies, basically it's the evolution of galaxies. So that's what we're going to talk about. So this is a very basic view of the cycle of matter inside galaxies, and I will go through it very quickly at first, and then we will speak about some of these elements more in details later. So the first element in this cycle is star formation in the interstellar medium, and when we see around, we see in the Milky Way, for instance, we see regions where we actually see clouds of gas collapsing and making stars. And we see some of this region in the interstellar medium with young stars appearing in them and then making holes in these clouds around them when they ionize the gas around them. And this is M16, which is a famous one seen by HST or by Herschel. And we see many of these regions, and people even model that. So this was my only occasion to put a movie in my presentation, so I put it there. So some people try to model this sort of region. They start with a cloud of gas and follow the collapse of the gas, put some turbulence in it and so on, and with some physics, of course. And when some material has been collected in a sufficiently dense area, they make a star. And it shows that we have an idea of how stars form, because when you look at this distribution of gas and the points, you see that in the end it looks like what we actually observe in clouds in the Milky Way, where the green and red points here are young stellar objects that we find inside nebulae. So this is the first step, and I will not speak much about it, but Denis will speak about the formation of stars in his lecture, so we will come back about that. Then inside stars, this is where the chemical evolution part occurs, when, as you know, the core of the stars reach temperatures which are high enough to have new nuclear reaction taking place. So you have the formation, for instance, of helium from hydrogen. Here is with the proton-proton chain. That is one of the ways you can have this reaction occurring in main sequence stars. And when stars get more evolved, their structure is going to change, and you can reach higher temperatures and have new reactions that take place. Helium can make carbon and oxygen, and you have this chain of reaction which is possible when you reach the highest temperature. And when you have, for the most massive stars, above 8 solar masses, you will reach a place where you can have made the iron in the core of the star, and in different layers you can make the different elements from different reactions. So this is the way in the stars you're going to have the stellar nucleosynthesis occurring. Then, of course, at the end of their life, some of these elements are going to come back to the interstellar medium, so it's going to be enriched. For the stars of intermediate mass, this occurs during a planetary nebular phase, which you have some example here, where the outer layers of the stars are ejected by winds, and you actually can see the different elements if you put filters for different elements, and you make some color images with that. And in the center, you have a white dwarf, which is left. And for the most massive stars, they will explode as core collapse supernovae. And well, this is how we look for supernovae, right? We look at the sky at different epochs, and when we see a new point, we know there was a core collapse supernovae, or a type of supernovae. During this instance, this is a very violent event, and the supernova itself is brighter. You see that the point is very bright, maybe not on the projector, than the full galaxy. So it's a very lightful event, and that's why we can use at least some type of supernovae like the 1A for cosmology, because we can see them very far because they are so intense. On the other hand, this type of supernovae is linked to the evolution of binary stars, not to direct the core collapse of massive stars, so I will speak of that when we get more into the details later. And finally, sometimes, maybe you don't have even an actual supernova that you can see, because the collapse of the core occurs when you have a sufficient massive core of iron that has been made, and if the outer layers rebound during the collapse, you have a supernova. But eventually, you can have also a direct collapse into a black hole, and this is maybe what has happened in this case, where at two different epochs, you see massive stars that have just disappeared, and we have not seen a supernova at that place. So that may be the formation, direct formation of a black hole without seeing the supernovae. And this is a slide summarizing this stellar evolution with the ends. You have stars of different masses here, the low mass at the bottom. I'm not sure you see very well. But basically, the low mass stars are going to not evolve much and stay on the main sequence forever from our point of view. Stars like the Sun will go through a phase of red giant, then a planetary nebula, and a white dwarf is left at the end. Massive stars, as we have said, make a core collapse supernova, and eventually you are left with a neutron star for the remnant in the center, or a black hole, and eventually you can directly form this black hole. And during these phases, all of this is going to go back to the interstellar medium and enrich it. So you've been around the cycle, which I will put again here, and during this cycle, well, these chemical elements that have been synthesized in stars are going to be mixed and go back. Now here I have complexified a bit the picture just to say that, of course, the evolution of galaxies is not as simple. First, the kinematics of the galaxies is going to influence what happens during the mixing phase, during star formation. And also there is all the interactions that you can have with a cosmic web, accretion of gas along filaments, interaction with other galaxies, ramp pressure, stripping in clusters, and many other physical effects that can occur. We can model them, but in what I will present here, I will go through the relatively simple case where we neglect these sort of things, just because it allows to introduce many concepts which are useful. Okay. So before going into more in details, I make a little bit of parenthesis. This formation of the elements in the stars is actually something that has been not known for so long, because it's in this paper, which is quite famous, by Burbidge, Fowler, and Hoyle, that they made the computation showing that you can make all these elements in nuclear reactions when you have high temperatures in the core of stars. And so this paper is quite famous, because before that we didn't know really where the elements we are made of were made. And so it was made in 1957. So if you compute, that was 60 years ago. So it's only 60 years ago that we have understood that. And interestingly, it occurred at the end of a decade where people started to wonder about it, and Salpeter, the name that you will hear for other things, had suggested that since we see carbons around Earth, there must be a way to make it, and the way to make it was to put 3 helium nucleus together quickly, because the intermediate step is not stable, and so you can make that. And that these suggestions motivated some works by these guys, basically, both theoretical and in the lab, to measure states of elements, to check nuclear reactions, and to show that it was possible, and led in the end to this full vision of how you can make all the elements in stars. So a last thing about history is that one of the authors of this paper is Fred Hoyle, which is an interesting character. And probably one of his motivations to work in this field, to make the elements in the stars, was that he didn't want the elements to be made during the Big Bang. Because at that time, people were wondering, is it primordial nucleosynthesis? Is this made elsewhere? And Hoyle didn't like the Big Bang because it looked too much like creation, And he was not very fond of this idea. So it's actually him that called it Big Bang from on a BBC emission to mock the term. Maybe you know that already, this story. And so he was motivated to show that you don't need the Big Bang, you can make all the elements in the stars. And in fact, from this work he's contributed to, indeed, most of the elements are made in stars, but the most abundant ones are you still need the Big Bang to make them. They are not made in stars, hydrogen and helium. That's a little story. So even if his motivation was maybe his profound belief, he still contributed to science, but he had to stop where the science results are, right? It could not go further away. Since I've noticed there is some geek in the rooms, we have been talking about Star Trek. I've seen some Star Wars t-shirts also, I think. So I wanted to mention that Fred Hoyle is also a science fiction author, which is kind of original. I've read The Black Cloud, which is one of his famous books, and if you are an astronomer, it's kind of interesting to read it. You can tell it's been written by an astronomer. I've not read the other one that I put it here, and I just put it because there was a connection with a school t-shirt, so I thought it was fun. Okay, so now I'm talking about things that date from 60 years ago, so maybe you think this is old stuff. We are young. We don't care about old things. So I'm going to show you that actually chemical evolution leaves traces of the evolution of galaxies that we can still, that are important and that we can use today to understand about galaxy evolution. So these are a few examples of what the traces that are left and that are linked to this chemical evolution scheme and that we can use to better understand the evolution of galaxies. So here is some examples from measurement of abundances of, in this case, iron and of other elements in stars in the Milky Way. And for instance, we can measure the distribution of abundance of iron in the halo of the Milky Way or in the disk of the Milky Way. We can do that in other places too now. And obviously they are different, so this is linked to the history of the different components of the galaxies. And we can use that to decipher what has been the history. Why are they different? And in a similar way, you can look at the ratio of many elements to iron. And you can see, for instance, that the oxygen has a trend here, which you don't find in other elements. And this is with respect to the iron, which increased during the history of the galaxy. So this is also telling you something about the history of the galaxy. And we will see a bit what it can tell you. Another example is abundance gradients. We can measure in nearby galaxies abundance gradients, mostly in H2 regions where the gas is ionized, and from the analysis of the line, we can derive the abundance of oxygen in this case. I will speak a bit more about that later. And this is an example in M33, but we can do that in many nearby galaxies. And there is gradients like this, so the abundance decreases with radius. And this is probably telling us something also about how galaxies build up and grow, because to have higher abundances, you must have more stars that have been producing oxygen, so higher level of astration, or more stars, relatively speaking, have been made in the center with respect to the outer. So that tells you how star formation progress in the life of a galaxy. And this can be done in many galaxies, as I said. So here is the value of the abundance of oxygen at a given radius characteristic in galaxies as a function of the type, of the magnitude, or of the rotational velocity of the galaxies. And there is some trends, which maybe are not very nice here, but you can find maybe more recent work with mass metallicity relation where you will see nicer trends even. And in below, it's a gradient. So it's this variation with radius that I was speaking about. And in this case, it's normalized by the size of the galaxy. And here you can see that it doesn't depend so much on anything. So that probably shows that first there is difference between galaxies depending on how massive they are, more or less. But at the same time, this difference is probably an evolution which is homologous. Well, so bigger galaxies have the gradient which is flatter, and so it kind of compensates each other, so that when you normalize by the scale length, it's they are kind of similar. So this also tells you about the evolution of galaxies. We can do that now even in high redshift galaxies, and especially I'm showing here some examples of high redshift galaxies which are lensed, because you need some lights to do this sort of measurement, and especially if you want to measure different places to have a gradient, and you need also some spatial resolution. And so it has been done in lensed galaxies where you reconstruct where was the light coming from, and you measure this line emission, you derive the abundance, and you can, here there is two examples that were found early on of what was the gradient. So yeah. The blue and the red points. And the other lines are basically models of the evolution of galaxies, which are made for redshift 0 galaxies. And so, since at redshift 0 we predict what must have been their history, we can check that our models were right or wrong and which one will work better for this type of galaxy or not. So that was just one galaxy. Sorry. But now we can do that in many more. So there is some recent works about that. Here you have again this metallicity gradient as a function of the specific star formation rate. We will see later what it is, I guess. But the main message is that the gradients that we saw early on in some galaxy, I think it's this one. And so the more recent measurements tend to be kind of clustered around zero gradient. So maybe the gradients are flat in this sample of high redshift galaxy from the KMOS 3D surveys. So now we can make this and we have new indication. Of course, it's complicated because, as we will see, the metallicity measurements are not easy. There can be some mistakes, some errors. And also, we are looking at faraway galaxies, so beam smearing effect or images, and you have to make corrections, and how you make them can change a bit your results. So it's still preliminary, but it shows you that we can learn some things like that. This is another example of chemical evolution in the big spiral in the nearby universe, the Milky Way, M31 and M33. And the thing is that I talked about abundances mostly, so you have them here again, the oxygen to hydrogen ratio. But we can also constrain this type of models by the other quantities, which are the gas distribution, the star distribution, the star formation rate distribution, the gas fraction, all of this as a function of radius. And all of these together give you constraints on what must have been the history of these galaxies, of our galaxy and our neighbors. And finally, I talked about individual galaxies, but we can also talk about the cosmic chemical evolution. And it's basically very similar, except that you, instead of looking at one galaxy, you average over very large scales. And we can nowadays measure star formation rate density average over large scales in large surveys. This has been done by many teams, and you have it's a Madao plot basically, where you have the star formation rate density as a function of redshift with a decrease after redshift 2 and maybe something like this beyond. And we can also measure the stellar mass in large sample of galaxies as a function of redshift. So we have the star formation rate, the mass. We can measure abundances, for instance, in absorption in distant quasars. I will show a bit about that. And we can measure also the gas, the H1, for instance. So, in fact, we can have all these elements of the cycle that I showed at the beginning on cosmic scales. So, it's also a subject of cosmic chemical evolution. And you can look at the review of Madao Dickinson if you are interested by these aspects, for instance. Okay? So now, this was kind of introduction material, and now we're going to get into a bit more technical things on this subject. And I'm going to talk a bit about how we measure abundances in some cases, because I think it's good that you have this sort of thing in mind if you later work with metallicity measured in some way, that you know a bit where it comes from. And that you know a bit also about the notations that you will find in papers, because there is many ways to talk about abundances and metallicity. And sometimes some people get a bit confused, so I thought it's useful to have one slide about that. So what you can find sometimes is just the mass fraction, which is often written x. So that would be the fraction of mass, which is in the form of metals. So if you look at a given element, you will have the fraction of mass in the form of this element. Traditionally, we use X for hydrogen, Y for helium, Z for everything else, so that the sum is 1. But then you can also look at different elements with their fraction. Here you have the values, the current values for the solar mass fractions of hydrogen, helium, and metals. And I put them here because they have been revised in 2009. So if you look to old papers, here Z is assumed to be 0.02. But the more modern values are quite significantly lower. And since we use the solar reference in a lot of work, you will have to be careful about which reference they used if they give you something in solar units, because this may have changed in time. So you should be careful about that. Something else that we use sometimes is just the number of given elements, so it's not by mass fraction but by number, and if you look to the ratio of different numbers, it's a number fraction, so you will have a difference between mass fraction of element depending on the mass of the atoms, right? And for instance, it's what we use when you find notation like 12 plus log O over H, which is a very weird scale, and the 12 is just so that because the difference between the different elements is in the factor 10 to the 12. So for most elements, you will have something, positive numbers if you use this scale. So it was introduced at some point for this reason. It's quite arbitrary, but you have to live with it. And as I was saying, we also use very often things in relative to solar. So that can be either just the global metallicity divided by the solar one, or eventually you find sometimes this type of notation with brackets. And it's the ratio between two elements, and it's their logarithmic ratio minus the same thing for the sun. So it's still relative to solar. And this is very typical of what we do in the Milky Way. So some of the plots I've shown you, you already had seen this type of notation. So the iron goes between, in the stars that we observe, between -5 and 0 or something like that, a bit more. And the oxygen to iron ratio, you will find it's between 0 and 1 in these units. Okay. Now, how do we actually measure that? So I show abundances in the Milky Way derived from the stars, so I'm not going to detail very much about that, but we have models of the atmosphere of stars, and if you have the spectra with high resolution of some stars, you can just compare them to models for different metallicities, and you're going to derive the abundance in the star of this element. Then there is other techniques which you can derive, for instance, the average metallicity in a stellar population for a full galaxy. And that you can do it by comparing, well, the spectra of the cumulated stars of the galaxy. And so this is more about stellar population synthesis techniques. So Véronique will talk about that, and I will not speak much more of it. And then you can measure by in the gas, so the abundance in the gas. So measuring the abundance in the stars is interesting, but usually you're going to have an average abundance over stars of different generations if you have the second one that I put here, right? So it's not like the metallicity right now in the interstellar medium. So in the gas, at least you have the current metallicity, so it's not average over some different age and things like that. So it's interesting. We can have it in emission, and I will come back to that later on. And I wanted to mention also this absorption techniques, which is very efficient for high redshift. And what happens is that if you have a distant quasar and you look in this direction, if there is a galaxy on the line of sight, like here, the gas in this galaxy is going to create absorption with respect to the background light. And so in the spectra of the quasar, you're going to have absorption lines. And you're going to have lines due to hydrogen, which are you find here. And from time to time, you can even have what is called the damped systems, where you have a very large H1 absorption, and that typically means that you have a large density of gas, a large clump of H1. And usually you can measure, for the same redshift, lines which are due this time to other elements. And so from this analysis of these lines, you can derive abundances for some elements. Not for all, but at least for some. So that's a powerful technique to go to very high redshift. And in the gas, we can measure abundances from in emission. And this is some example of spectra that you can have of star-forming regions or galaxies with a lot of star formation. And there is many lines, and basically the ratio of the lines that you observe is going to be related to the abundance ratio, so that's what we are interested, and to atomic properties, which may depend on some physical properties like the electron temperature. So if you have observed many lines, some of them are going sensitive to the temperature, and you can get it, and then you can get the abundances by applying this sort of relation. However, in many cases, in galaxies, you cannot measure as many lines as you want. And in the worst case, and especially if you look at distant objects, you will have only the strongest lines that are going to show up. And so you will have this sort of indicators which are based only on few strong lines. So this is one that was very popular, so you will find still some works with that, the R23, which is basically oxygen 2 and 3 combination of lines related to the H-Balmer line. And it has been calibrated when you can actually measure also the other lines. You derive the proper metallicity, and then you can compare this indicator to this actual metallicity, and you find some relation. So here it's obvious that if you have a good idea of the abundance of your galaxy and you think it's high metallicity, you will be able to determine it with that. But you can see that there is a double branch, so it's degenerated for some values. So other calibrators have been proposed. Of course, it means you need to be able to have these different lines to resolve them, to measure them, based on nitrogen to H-alpha ratio, for instance, or oxygen to nitrogen. And you can see that these sort of things have been calibrated in many cases. Well, they've been calibrated, but none are really perfect. So this is a work which is useful to know also, the Culey and Ellison paper, where they compared basically the relation that you find in galaxies between the mass and the abundance of oxygen, depending on which calibration you use to derive the metallicity. So there is a bunch of them. And depending on what you have, you can see that there is a lot of difference. So you can see that it's going to change the absolute value can change from 0.2 to 0.3 dex. So it's quite significant. It means you never have, or you rarely have very accurate global metallicities. But on the other hand, as long as you use the same indicator, usually you find similar trends. So, for instance, in the mass metallicity relation, and it would be also true if you look at abundance gradients, the various indicators show you the same trend. So the absolute value shifts, but you can still find the same trends. And this sort of comparison is useful to know the uncertainties that you have on what you're talking about. All right. Okay, so now this being said, I'll try to show you a bit more about the formalism of chemical evolution to handle a bit things. Here are a few references that you can look at if you want some proper textbook. You have the Pagel or Matteucci books. There is, I guess, the first paper really introducing this sort of things is Tinsley. And you can also find some other lectures like the introductions that have been made for lectures like this. This one is by Pransos, who was my supervisor, so that's why I put him. Okay. So I've described this cycle of chemical evolution with the ants, and now I'm going to try to show you that it's quite easy to manipulate with actual equations, but not very complicated one. So here are the various quantities that we will use, and one of the main points of departure is that we form stars from the interstellar medium, right? That's what I said at the beginning. So we're going to have to describe how stars are, and at formation. So we introduce two quantities. One is the star formation rate, which I already mentioned passing by the way. And that's just the amount of material that goes into stars at a given time, and that's in solar masses per year, usually. And you want also to describe, since stars of different mass evolves in a very different way, as we have seen, you want also to describe the distribution of mass of stars that you have. And you describe that with the initial mass function. That's the number of stars per unit mass at birth. And when you put them together, you have a global description of the star formation process. And here you have just a little normalization so that it all makes sense, and you normalize the initial mass function between its limiting masses by this. And the limiting masses typically are between 0.1 solar masses to 100 solar masses. Then you can discuss about details. And now we are going to try to follow the evolution of the total mass of gas, the total mass, the mass in the form of gas, the mass in the form of stars. And we will meet some quantities, so I will try to introduce them as we see them, but you will have the presentation afterwards if you want to come back to this slide. And I'm going just to try to write down some of these equations. Okay, so that's the first one. It's a variation of the mass of the system, and you consider a galaxy or a piece of galaxy, a region of the galaxy, and you can write that the variation of the mass is just the inflow rate minus the outflow. So inflow rate is whatever accretes your galaxy, and the outflow is if you have supernovae with very large winds, they're going to blow away eventually material, and the galaxy can lose material. And I'm going to make the assumption, the most basic assumption that we can do, and which is a closed box. So your system is isolated, there is no accretion and no outflows. Of course, this is unrealistic in most cases, in most actual cases where you look at a galaxy. It's rarely completely closed. But in some cases, it can give you still some indication of some things. So it's good to do it, and it simplifies the manipulation. You can actually make some analytical computation in this context. So a second equation is what happened to the gas. And here is the same thing. There's a variation of the mass of gas. Of course, you find again the accretion and outflows, but that I will neglect. And you have two more terms now. One is the star formation rate. So it means that you remove from your galaxy some gas to form stars. So it appears here. And the second term, which is what is ejected by the stars. And so it's basically what comes back from the stars when they are at the end of their evolution, to simplify. And to do that, you can compute it with this simple integral, which is here. So you're going to integrate over the mass of the stars, over the full initial mass function. For each mass, you're going to go back in time at the time when they were created, the mass of the stars with this mass. And this is just going back in time from this factor, which is the lifetime of stars of the mass m, right? And so you take the star formation rate of this epoch. This is the amount of stars that are dying now, the ones that were created with this mass in this past at this time. And here is just what comes back from one individual star with the mass m, which is its initial mass minus what is locked in the remnant, in the white dwarf or neutron star. So as you see, it's not that complicated. You can have this thing for the gas. Now here we have another equation, which is for a given element. So it could be oxygen, since it's one which is very abundant. And you have a very similar thing, but here instead of the mass of gas, we multiply it by the fraction of this element. So this is the mass in the form of this element, right? And then you have the same similar sort of thing. You have what comes in minus what comes out. We're going to assume again here as a start that is basically nothing. And then you have a fraction of the mass that was in the form of these elements that goes into the new stars. And you have the elements that comes from the stars which are dying. So this is this term. And this term is a similar thing. You're going to integrate over the initial mass function, go back in time at the time when these stars were formed, take the star formation rate at this epoch, and multiply by something which we call yield, which is in here what comes back from a star of mass m when it dies. And you can decompose it into two terms. One term, which is what has been actually created by the star, the actual yield of the star, what it has done, synthesized in its core, plus what comes back that was locked in the stars when it was formed. So you're going to take the abundance at the epoch of formation of the star, and you multiply by what comes back from the star again, right? And here I have assumed that it depends only on the mass, but things can be complicated for some elements which formation need to have already some other elements. So it would be secondary elements that are going to depend also on the initial metallicity of the star, on the abundance of the star at the beginning. But for primary elements, you don't have this, and we just depend on the mass. Okay. Everybody follows? Good. Now it's time to make another assumption so that you can play afterwards. And the assumption is instantaneous recycling approximation, IRA, which is good for elements like oxygen, for instance, especially when you have large gas fractions. It works quite well. And it's good for oxygen because oxygen is made mostly in massive stars. So for elements which are made mostly in massive stars, that will work relatively well. And the assumption consists in saying that, as you know, massive stars evolve very quickly. So you can say they evolve instantaneously. So above a limiting mass, that we will discuss again, we're going to say that their lifetime is basically 0 with respect to the age of a galaxy or of the universe. Right? And so when you do that, you see that these terms become 0, so this term doesn't depend on mass anymore. You can take it out of the integral, and this, what comes back from the star is basically the star formation rate multiplied by a return fraction, which is just the rest of this integral, and that you can compute once and for all, assuming that you take a limiting mass for these massive stars. So you can decide to take, for instance, one solar mass, and if you look at what happens after 10 gigayear, which is a lifetime of a solar mass star, it kind of works. And in this case, you find fractions between 0.3 and 0.4, or something like that. And I will discuss a bit more of that afterwards, because it's an interesting point. So it means that you have computed that once and for all, and it's just a number. And so your equation has been very simplified because it's you don't have integral anymore. You have just proportional to the star formation rate. And for a given element, you will have something very similar, because your equation from before, which is here, it's the same. You can take out basically everything that depends on the time. You can take it out of the integral. And you can have this expression much simpler here, which is again the return fraction times the star formation rate, but this time you multiply by the fraction of the element you are considering, plus what has been formed by the star, and that's going to be again proportional of the star formation rate that you take out from the integral, and multiplied by a quantity which is going to be again called another type of yield, but this time it's the total yield, so integrated over the initial mass function. So you integrate over all the stellar masses what has been made by stars of this mass. And you can do it once and for all for a given element, and then your equation is easier. So it means that with this assumption, and if you are in a closed box, you can go back to the equations. So you will do it as an exercise for next time, of course. People think I'm serious, I think. And you will be able to find that there is interesting properties that you can derive. So one thing that you can find, for instance, is that the abundance of an element is going to be, if you take an element that was completely absent at the beginning, so this is the initial abundance, you say, for oxygen, there was none at the beginning, so it's 0. And so the abundance of oxygen is going to be equal to this yield integrated over the IMF of oxygen, multiplied by the logarithm of the gas fraction, with some minus signs, right? So the gas fraction is the mass of gas over the total mass of your system. And what's fun is that, well, I think it's fun, is that this relation is, so links the gas fraction and the abundance of oxygen, in this case, independently of what happened in the life of the galaxy. If the star formation rate was very bursty or just a continuous star formation rate or with a peak or rising, whatever, if you know the gas fraction and the abundance, they should be directly related. So that's an interesting property of the closed box assumption. So now let's make one more assumption, and that is that the star formation rate is just proportional to the mass of gas. And this is inspired by observations that we will see in the next lecture. It's probably not exactly true, but this is something you can put in the equation, at least to play with them. And then you will find that you can have analytically the evolution of your system in terms of gas fraction and metallicity as a function of time, and where you will see only appear this return fraction and this yield, and eventually the original abundance if you take an element which was present at the beginning of your evolution. Okay, so you can compute that very easily if you make this sort of assumptions. So you can, if you want to play with these equations, I encourage you to do it. You could also try to put some more realistic laws here, and if you get interesting results, please let me know, and we will see what we can do with them. Okay, so now let's go to other case where you can do this sort of things. I'm still going to be using this instantaneous recycling approximation so that you can do analytical work. But of course, everything you can also do in a numerical model, and you should find the same when you make the good assumption. You can make also this analytical computation with other assumptions. And so here are two solutions that you can also find. In two cases, one is that you assume that there is accretion because an isolated system is, for a galaxy, maybe it's not very realistic. We know that galaxies grow in time. And we know that some galaxies accrete material. And one way to make it easy in the equation is to assume that the infall is just opposed to the star formation rate. And that means that it compensates the star formation rate. So your mass of gas is going to be replenished constantly. So this seems a bit arbitrary. But in fact, there is some models where or at least some ideas that people talk about, where in actual galaxies, it could be that the star formation is regulated by the amount of gas which is there. So it's a sort of self-regulation. So when you put gas in, it goes into stars with star formation rate, but just at the level compensating what has been falling into. So it's like some people call that the bathtub model, where you put water in, but what is overflowing is always compensating what you put in. Right? So it could be not so unrealistic. And if you do these assumptions, you can find also some relations which are a bit different, but you can check them and check that I've not made any mistakes here. And if you can also make another assumption, which is the case where there is outflows. And for outflows, if you decide that they are related to the winds of massive stars, since massive stars live a short time, as we will see, these winds will occur very quickly after star formation. And so you can think that the outflows are going to be proportional to the star formation rate. And so you can put that in the equations. And then again, you will find solutions analytically where you just have one more parameter which appears, and that's the efficiency of this of how much outflows you can make per unit of star formation rate. Okay, and you can make this computation. And now, in both cases, if you look at the diagram which is here, which is abundance versus the logarithm of the gas fraction, basically. From what I've said before, there is a linear relation here in the case of a closed box. And what happens is that with both infall or outflows, you're going to be affected with respect to that. And if you look at the form that you obtain here, you will find, for the same gas fraction, lower metallicity. So it means that if you are able to measure the two, and you find you are somewhere here, that's a good indication that your system have been having some outflows or some accretion. And I think I will show an example on how you can use that later. So now that we have written all these equations, it's time to talk a bit about the elements that we put in the equations, because All this is very nice, but I've told you the IMF, I've told you the yields, but what are they, right? So I'll talk a bit about them now. The yields, what is made by stars. So I'm not an expert of yield myself, so what I do is just take what is predicted by people making evolution models of massive stars. So here is an example from Huxley and Weaver. And they tell you, well, towards the end of its evolution, the star is structured like that, with taking into account all of the physics of stellar evolution and all of the nuclear reaction. And so you have some oxygen here, some carbon there, etc. And when you make a supernova explosion, you're going to take whatever is in the outer layer and blow it away, plus some other elements maybe can happen at this time. And this is going to tell you what are the yields. So you see that they depend heavily on theoretical work, and we are used to say they are probably uncertain by a factor 2, even for the more reliable of them. So for oxygen, for instance. And so this is for massive stars. And if you remember, I told you that the various indicators of measurement of abundances are also uncertain by a factor 2. More or less, 0.2, 0.3x. So that means that we are in a business where things are quite uncertain, and it's always, you have to be careful not to over-interpret. And the thing is that trends are more reliable than absolute value again, because if this is uncertain, anyway, if you do it in the same way for all the stars and for the history of your galaxy and for all your galaxies, you should find systematic differences. So the trends between different masses or in the gradients should stay. And then there is intermediate mass stars are going to also produce some elements which are especially important for CNO isotopes, some other elements, and they are also quite uncertain, but we can put them in the models also. And then there is another type of yields which I put here, and which are for these 1A supernovae events. So I talk about core collapse supernovae and models of massive stars and so on, but we know that there is quite some binaries in the universe. So this can affect the evolution of stars. And especially if you have in a binary star which evolves and make a white dwarf, when the secondary star is going to evolve in its turn, maybe it's going to transfer some material into this white dwarf that's going to grow. And when it reaches the Chandrasekhar mass, it can actually detonate and disperse completely in the interstellar medium during this event. And this is something that is going to produce a lot of iron, this event. Actually, this is just one way to do it. You can also have the merging of two white dwarfs, for instance. And if the result is above the limiting mass, same thing, you're going to have a 1A supernovae. And so this produces a lot of iron, and the problem is that you understand immediately that this takes time to happen, because you need to have first the evolution of the first stars and then the evolution of the second stars. So core collapse events, you can make the instantaneous recycling approximation, but for these elements it's not going to work because they occur after a delay. And here is, for instance, some work to compute the delay after which you would find these two types of events after star formation. So you see it's in billion years, so it's some of them are going to be delayed by 1 or a few even billion years. And so we have to take that into account. So in the chemical evolution models, it can be done either on implementing binary fraction and the evolution time for the primary stars and compute it properly. Sometimes it's made just by adding an iron source yield of 1A supernovae after a delay. And sometimes the rate of 1A is also based on this sort of equations, which is actually empirical. So if we, in this paper and some other more recent, people have been measuring the rate of 1A supernovae as a function of the properties of the galaxies in which they occur. And they found some fitting formulae where you can compute this rate from the mass of the galaxy and its star formation rate. So this is very empirical, but sometimes it's put in some models, and even if you compute it with a more fancy models, you can check afterwards that you reproduce this sort of dependence on mass and star formation rate. Right? So it's one of these things that we have to take into account. This delay for the iron is very important for some things that we can do. So this is an example that shows you the alpha to iron ratio. So alpha elements are elements like oxygens, which are a multiple number of helium nucleus, and they are just more stable, and that's why we call them alpha, and they are produced mostly in core collapse supernovae. And we distinguish them for this reason. And oxygen is one of them, so what you see here basically applies to oxygen. And this is as a function of iron. So oxygen comes from core collapse, and iron comes from 1A supernovae, which occurs after a delay. And here you have points from the bulge of the Milky Way, from the, which are basically these points here. You have points from the Large Magellanic Clouds, which are actually rather these points here. So you can see that they are not at the same place in this plot. And this illustrates one of the strengths of this chemical evolution analysis, is that it's probably related to the fact that these galaxies had different histories. Because if you make a lot of stars very early on, right, you're going to have most of your stars, and it's measured in stars actually in this case. So most of your stars are going to be more rich in oxygen than iron because of the delay, you formed everything before the release of iron, right? So you are high here. So here you have a scenario which has been computed for the bulge and which is assuming intense star formation early on and then not afterwards. So the iron comes very late in the history of the system, so this decrease happens late when the iron starts to come. And on the other hand, here you have histories which are adapted to maybe Magellanic type of galaxies, where the star formation is much more progressive. So you form early on some stars, but not so many of them. And then after the delay for 1A supernovae, the iron comes in, so it starts to decrease. And then it's more progressive. So instead of having a break very far, you're going to have a progressive decline of this ratio. So that shows you that this chemical trace tells you about the history of the system. And we can use that to guess what must have been the history of the bulge or of the Large Magellanic Clouds or of DLAs like they were trying to do in this paper. Okay, some other elements that are important. I was talking mostly about yields up to now, but all that we speak about heavily depends on the properties of stars. So I already mentioned actually some of them, and this is just the occasion to remind you them. So here, for instance, you have the lifetime of stars as a function of their mass. So you can see indeed that the massive stars have much lower lifetimes than the low mass stars. Here the scale is logarithmic. Here we are at 1 million years. Here at 1 billion, 10 billion here, like where is the sun. And for low mass stars, it's almost eternal. So this justifies that we can make this IRA type of approximations because there is so much difference between those type of stars. Here at the bottom, you have the remnant fraction. So that's a fraction that stays locked into your white dwarf or your black hole or your neutron star. And it shows you that the fraction is high for low mass stars. In fact, For very low mass stars, since they never really evolve, it's 1. And then for massive stars, it's lower. And usually this, you don't find very much about it in publications. And this is also quite uncertain because we don't really know very well the fraction of stars or at which mass that's going to make a black hole directly, for instance, or the mass of the black hole that stays after the evolution. This is quite uncertain, but still we use standard values. But it's another factor of uncertainty, I would say. And then here is the initial mass function. So the massive blue stars are made in very small numbers. They are still extremely important. And the low mass stars are made in very large numbers. And I'm going to spend a few minutes to talk about this IMF. And to talk about it because it's very important for many of the things that you will do. And it's the occasion to say a few things which may be important. So here is the initial mass function. So here you recognize it's the same diagram as before. So it's different reference. One is salpeter that I was mentioning before on a completely different subject. The Chabrier IMF, which is very popular right now, and then there is some Krupa IMF, the 2001, which is not so different actually, and an older one, which is a bit different. And on the bottom panel here, you see it's as a function of the mass of the star. You see the ratio between any of these IMF to salpeter. So, first point, you can see differences. And these differences are going to be important because in the low mass range here, this is a fraction of stars which are just locked. They don't evolve, they have very long lifetime. So when you put mass in there, it will just stay there. It never comes back to the system. So it has an influence on the chemical evolution. And you can see there's some difference in this low mass range. From the light output, and I will not discuss that, but in other lectures it will be discussed, it plays a role also because, of course, a lot of light in the red part or near-infrared part comes from this low mass range of stars. Because there are so many of them and because they are red, they're going to affect this range. Then the intermediate mass stars, they are an important light provider. And they are especially during some phases. And on the massive stars, they are also extremely important. And here again, you see some differences. And they are important because it is the light coming from the massive stars that we use to measure the star formation rate, as you will see with Veronique, I think. And this is because they have short lifetime. So when you measure that, it's close to the time as they have been formed when you see the light coming from massive stars. However, you see that the IMF is going to make a big difference. They are also important for the output of metals and especially for oxygen. So, of course, it's going to make big differences here, this difference. So now that this is said, the difference that you can see is that first let me start by salpeter, which is the horizontal line by definition in this plot. And you can see that it's different from all the other ones. And the reason is that, in fact, the salpeter IMF was really measured early on, in 1955, in a limited range of mass, of stellar masses, and it's been extrapolated. So now everybody still uses it because it's a reference, but you have to realize that when you can measure the IMF directly, usually it doesn't look like salpeter, especially there is a flattening at low mass star, at the low mass of stars, and this flattening is found by almost everybody. So in relative terms, you have this difference here, right? And for the other ones, you can see that, as I was saying, in relative terms, Krupa and Chabrier are not very much different, and they both represent this flattening. And the other Krupa one, the older one, is very different in the massive end, and that's going to make a big difference in metallicities, depending on which one you use. And currently, the Chabrier is favorized, I would say. Most people use this sort of IMF, which has been kind of confirmed. But you can still have some differences, and it's not a definitely chosen one. Here you have also a table that tells you values that have been proposed in the literature to convert from one IMF to the other one in terms of measurement of star formation rate. Because as I said, of course, if the massive end is different, you're going to, and you measure something coming from massive stars, you have to assume an IMF to derive the complete star formation rate. And depending on the one you assume, you can see factors that goes from 0.8 to 1.6, right? So that's also something to take into account when you measure star formation rates. And finally, on this slide, I also put here this plot, which is a return fraction. So you remember that I've defined this return fraction early on, a few slides ago. And that's when you make the instantaneous recycling approximation, you decide a limiting mass, and you say above this mass, stars are die instantaneously, and everything comes back. And when you do that, I told you, you find 0.2, 0.3, 0.4, something like that. So here is actually some computation of this fraction, depending on the lifetime of the stars that you adopt to make the separation, and depending on the initial mass function that you adopt. The same color code as here. So first you can see that this return fraction is 0.3 for here for if you adopt 10 gigayear separation. And this was the separation between the massive stars evolving instantaneously in the other one. And this is a value that is typically adopted when you make this sort of chemical evolution in the Milky Way, which is very old, and so you want to have this difference between stars that have been created in the long past and stars which are created now. And so you find this 0.3, 0.4 for Salpeter IMF or Krupa 93 IMF. But if you take another one of the IMF, you find a larger value, which can be 0.5, so it's kind of a bit different. But also you can see that this value also depends a lot on the limiting mass or the limiting age that you adopt. So I said that when you are in the Milky Way and you want to make a separation at 10 gigayears, that's okay. But now if you are looking at high redshift galaxies and you say, oh, the return fraction is 0.3, this is going to be completely wrong. Because if you are in the high redshift universe, maybe the universe is only, I don't know, depending on the redshift where you are, you can be at very early in the past, and you can see that there is an evolution of this return fraction. And if you adopt 10 gigayear, well, as a limit, none of your stars have reached this point in reality, so you are overestimating your return fraction. So you should also take into account that this return fraction may depend on that, and eventually you could adopt a time limiting the different type of stars, which is adapted to what you are studying. Another point on the initial mass function that I wanted to mention is this question that comes back very often, which is the IMF universal, constant in time, or not? And this is a question that I will not answer, because on a regular basis people say one thing and then the contrary. It's a bit like when you have a new observation and it doesn't fit so well, you say, yeah, maybe the IMF is changing, and then whatever. Anyway, you can look at the review of Bastien et al., which was kind of favorizing a universal IMF, but there is a lot of discussions, and I'm not going to get into all of them. I wanted still to mention these relatively recent ideas that have been developed by Weiner and Krupa and their collaborators, which are the idea that the IMF should actually depend on the star formation rate. And the reason is that if you look at a galaxy, you see that star formation is occurring in clusters. And if you think about it, the most massive, so you should first integrate over this population of clusters. And the most massive clusters you can have probably depends on the star formation rate, right? Because, so it's here. You integrate over the cluster mass function, and you adopt a limiting mass for the maximum, the biggest clusters that you can find. And of course, if you have a star formation rate of 1 solar masses per year, you don't expect to have a gigantic cluster of I don't know, 10 to the 4 solar masses. It's just a question of how much material you put in stars. You can make a gigantic cluster if you don't have much star formation rate. And so they try to fit this maximum mass by this formula here, and they integrate over the cluster population. And inside each cluster, there is the same phenomena. You can integrate over the initial mass function inside the cluster, and you will never make a star which is more massive than the cluster. So there is also a maximum mass of the stars that you can make, which is function of the cluster mass, and this is represented here. So when you put all of this together, you will obtain what is shown here, which is that the Krupa traditional IMF would be this envelope here, but depending on the star formation rate, since you cannot make the most massive clusters and the most massive stars in them, it's going to deviate from it, and depending on the star formation rate, it's going to deviate more or less. So this sort of things has a lot of implication. For instance, it has been used to try to interpret the differences between H alpha and UV emission in some galaxies. Why? It's because H alpha is due to the ionization of the most massive stars, and the UV emission come from stars which are a bit less massive. So you can make a variation in this ratio by changing the IMF. And it has been discussed a lot. It seems logical on a first basis, but then it's a question of the chicken and the egg. Is it really the star formation rate that sets the maximum mass of the cluster, or is it that you form cluster with this maximum mass that kind of fix the star formation rate? So I think it's still quite debated, but it's an interesting idea anyway, and I wanted you to know it. And then there is also the question of evolution with redshift. As I was saying, when you find things that don't fit too well, you say maybe it's IMF. And so some groups had found in the past that the evolution of the star formation rate that we measure in large surveys, if you integrate it, you didn't find exactly the evolution of the stellar mass density. And you should. It's directly related. And so there was some suggestion that this was an IMF effect. But more recent work seems to indicate that, in fact, it's been redone with more modern templates and so on, and it's kind of consistent with each other now. So probably it's not worth to worry too much about that. Okay. So I'm going to stop there on the IMF, because I think you have already things to think about. And the last thing for today, I will speak a bit about the galactic ingredients that I've mentioned in all of this, because previously was the stellar ingredients, but now there is some galactic ingredients, which are maybe what interests us most, because, okay, the stellar properties, it's the guy studying stars that tells us, but what happens to galaxies, it's what we want to find. So I will come back a bit on some of them. So, first, about this story of accretion, about infall. I mentioned that we have some signs of that the galaxy accrete material and so on. And actually, we even have in the Milky Way, it was introduced the infall very early on in this type of models because of this distribution of metallicity that I've shown you. And here you have a schematic view of this thing. So if you are in a closed box model, and you put some gas with a star formation which depends on the gas without entering into the details, you should, if you have a lot of gas from the beginning, you make a lot of stars at the beginning. And these stars, they have not yet been enriched in metals, so they're going to have a low metallicity. And then they're going to enrich a bit the gas around them, but since it's a closed box, there is not so much gas, so there is less stars that's going to be made with this higher metallicity, and so on. So if you actually put that into the equation and into the models, you will find the distribution of metallicity expected, which is a dotted line here. Now, if you say that you start with no gas, and you just put a little bit of gas at the beginning, and you're going to bring the gas progressively, so it's an infall, an accretion. Well, your system at the beginning has very little gas, so it makes little amount of stars. So you have few stars with low metallicity. And these stars enrich the gas around them. But at the same time, you accrete more gas. So you're going to be able to make more stars afterwards. but you make them when the metallicity has been already enriched, and so on. And then when you do that and you compute it, you find a distribution that look like the solid curve, which is consistent with the distribution of metallicity of iron that is found in this distribution of metallicity that is measured actually. So this was I think the original idea to put infol in such models was coming from that, trying to solve this distribution, this problem, this G-dwarf problem, because the dwarf stars in the solar neighborhood had this high metallicity, and you could not do them with a closed box model. So that was the original idea. There is actually other elements. For instance, if you look to galaxies, and we will see that later, you find clues that they must have not been formed very early on. But I will come back to that a bit afterwards. Before it, I wanted to say that this view has been a bit challenged in the recent years, and especially stellar migration can quite change these pictures, because here you assumed a closed box at a given place, and then the picture I was saying was okay. But if you have stellar migration, the stars can change radius in the Milky Way. When you look in the solar neighborhood, maybe you have stars here that were formed in a few kiloparsec inside the Sun, where the metallicity is higher. So maybe this distribution is not just the simple effect of infall or of accretion, but you also have migrations that change the picture. And eventually in the last lecture, if I have time, I will show you some example of that. So this question is not completely solved. What I was saying about other signs of accretion is shown here. This is also sort of an old story, but there is more modern view that will tell you something similar. And that is based on observations, so I'm not going to get into the details, because Veronique will explain you better how you can measure the star formation rate and the stellar mass in galaxies. And from these observations, you can derive the specific star formation rate, so the star formation rate per stellar mass, and a quantity which is more linked to the chemical evolution is the ratio of the star formation rate to its average past history. Okay? And if you use approximations that I mentioned earlier, you will find very easily that the two quantities are directly related. And so it means that if you have a high value of these quantities, in a way it's an indication that the star formation rate now is higher than it was in the past, so an increasing star formation rate. And if you have a low value, on the contrary, it means that it was much higher in the past, and you can have all the intermediate values. And these basic observations helps you to guess what must have been the history of star formation of the galaxies. And you can also have an observation which is directly related to this B parameter, and that was done a long time ago. And it's the equivalent width of the H-alpha line. And the idea is that the H-alpha line, it's related to the massive stars, so it's star formation. But when you make the equivalent width, you normalize by the continuum, and that's the old population of stars, the continuum. So this equivalent width is basically sort of equivalent to this B thing from an observational point of view. And people have noticed some time ago that this value depends on the type of galaxies. So it tells you that the different type of galaxies must have different history of star formation. And here it's what is shown in this panel. Here you have time. This is a plot from Alan Sandage, and I didn't put the date, so it was some time ago. And it's a sketch, basically. It's a sketch of what must be the star formation history of the different type of galaxies to reproduce these sort of things. And in the top panel here, you have the early type galaxies, elliptical, S0s, S8s, where you find very low value of this thing. So it means that the star formation rate was probably very high in the past, a long time ago, and then decreased and went to low values. You can look at paper by Thomas, Marston, and collaborators to find more modern views of this sort of things, but you still find this sort of things. And here it's late type galaxies, and where you have again SA, SB, SC, SD, and Magellanic type galaxies. And in this case, well, for later type galaxies, you see that you need to have larger values of these values, larger value of this current star formation rate with respect to the past. So you must change your shape of star formation history to get something like that. And here again, low mass late type galaxies must have this maybe rising type of star formation in some case, and the opposite for early type. So basically that's that, and to explain that, you must think that these late type galaxies, why should they not make the star very early on like the other one? And the simplest explanation is to think that there is an accretion that has been progressively building the galaxies. So that's another sign of the past history of accretion of galaxies. And then there is, of course, much more modern ways to do this sort of things nowadays. And Veronique will talk about set fitting and see how you can do this sort of things. Of course, the accretion the accretion history of galaxies, you can also derive them now from cosmological models, because, and it's not my lectures, but you have probably seen these simulations where you see the accretion of dark matter halos in which the baryons must follow. And if you follow this history of accretion of the halos, and if you think baryons follow them, it means that galaxies also accrete material little by little. So that's also a simulation evidence for this sort of things. Now, just a few words on outflows on the other end, because I also completely neglected them in the equation most of the time. But we know that outflows exist. This is an MT2 galaxy in the nearby universe. Google it to have a better quality on your screen. And this is a disk galaxy where you can clearly see H alpha emission, which is blown away from the center of the galaxy on each side here. So it means that this galaxy is obviously, and we see it, losing material. And that's some sort of winds of outflows, which we see. So they exist, and we see them in the nearby universe in these sort of things. Now I wanted to remind anyway, on the other hand, that this is MT2, and this is probably the most spectacular case in the very nearby universe. And this is a galaxy image. In the same field, you have M81, which is a much more massive spiral, and you don't see this sort of thing. So you see them in this relatively small star-forming disk, right? But in M81, which is a more massive, you don't see it. So a possible interpretation of that is linked to the fact that outflows don't occur in all, maybe not in all galaxies, at least in the nearby universe. And actually, from what I presented before, I can show you an example of how we can guess that. So this is a work that has been done in 2002. You remember this, of course. You will demonstrate it as an exercise for next time anyway, as we said before. And so this is the relation between the abundance and the gas fraction. And in nearby galaxy, you can measure this sort of things. You can measure both the gas fraction and the metallicity. So if you do it, if you are in a closed box, you should find here the yield. Now what he did is to say, remember, in simple models you have a direct relation, but when you have outflows, you will go down here. So what I can do is define an effective yield so that this relation holds. And if the effective yield is a real one, it means that I'm in the simple model. If it's reduced, it means that we are in the presence of outflows. And this is what he did for a sample of galaxies, nearby galaxies in this case, of different rotational velocity. So that means that here is very massive galaxies. The Milky Way would be somewhere around here. And in this side are dwarf galaxies. The large Magellanic Cloud would be somewhere around here. And he found that the effective yield indeed has a constant value in the massive galaxies and seems to decrease in the low mass dwarf galaxies. So what he deduced is that probably outflows in the nearby universe occurs in dwarf galaxies because they are small, so the potential well is not so deep, and when you have winds, they can escape the galaxy easily. But on the other hand, in the massive end, when you have the same winds from the supernovae or from the massive stars, they are going to be, they cannot escape the massive galaxies and will stay in there. And so that would explain this different type of trend. So this is a sign that outflows in the nearby universe are probably frequent in low mass galaxies, but not in high mass galaxies. And we can also, of course, study outflows in the distant universe. So we do it in a different way. And this is just an example, but basically you have the idea here. If you have your galaxy and you look it from somewhere here, when you look at the galaxy in emission, you will see the disk, for instance, of the galaxy. If you look at something that is directly linked to the galaxy. And now if you look in absorption, because you have a line of sight in your direction of your galaxy, you can see maybe some clouds which are coming towards you and that's going to shift the absorption with this Doppler shift, and some clouds which are in the back and that's been blown away towards the back and goes the opposite way. So you can look at the difference between the emission and absorption lines in distant galaxies, and you find this very large values, very large gap. You see 600 kilometers per second. This is too large to be something happening within the galaxy. So it's a good sign that these giant galaxies at high redshift are having outflows. So you can look at this reference, and you can look also to some modern work discussing the evolution of outflows with redshift. So there is a lot of work being done in this field, and it's extremely interesting. Okay, so there is a last ingredient from the galactic point of view that I have not discussed today, and that's the star formation rate. And obviously it's very important because it's very central to the evolution of galaxies. And so what I will do is extensively talk about that subject in my next lecture. And for today, I'm going to stop here so we have time for a few questions if you have. Thank you.
A minor comment in the question. The minor comment is, of course, Fred Hoyle actually, who said Big Bang. He was in Milano, by the way. And I don't think he was so much concerned about the explosion. And he was eventually concerned with the singularity because created matter, the paper you mentioned by Margaret and so on, is related only to nuclear processes,
yes,
especially the air process. And so, in fact, in the steady state, Fred Hoyle wanted himself to create matter, because otherwise he wouldn't keep the density. So the problem was a little bit...
The singularity aspect.
The question is that I worry a little bit, you always, all this, I know it's a general question, and in fact I think probably Francesca Matteucci would also worry about this, but I am not in the field. Now, you always use for metal abundances oxygen, okay? And then actually in one of the first one, you did show both oxygen and the other one, by I wrote the name, whoever wrote this, Peru, 2012, he used iron. So
okay,
again, I mean, are two different indicators. Then, of course, you show it in, I kept on because, so I remember the plot by Francesca Matteucci, where you have the alpha versus iron, and there is a big scatter. So, what nobody ever shows is, what I would like to see, is a plot of oxygen versus metallicity in those few cases where it can compute it properly, and by metallicity I mean Z, or iron versus metallicity, and again I mean Z, because this difference indicator sometimes might not reflect at all metallicity, because for instance you mentioned later on in about the consequences of the initial mass function, and you precisely said that in fact is a problem because may produce, depending on how it goes, may produce more oxygen. So then if I use oxygen as a metallicity indicator, I'm doing really a mess.
Yes.
So,
So the short answer is yes. It will be a mess. The thing is that so there is not many cases where you can actually put together all the elements and have a real metallicity. So like in the Milky Way, indeed you can measure wrong manipulation. Maybe this. Yeah. So in the Milky Way, you can have stars when you can measure actually many elements, and then you can measure a metallicity. That's where you can do it, and you find indeed some differences and some scatter and some trends, and I think you can, in a way you rely on that to say, okay, I can see that all the alpha elements behave sort in the same way, so I can use one for the other one. So after you mentioned Peru, and that's absorbing systems. So that's a big problem, because in absorbing systems, you cannot measure oxygen. The question is that the lines are not adequate, so you must measure some other elements where you can do it, and so they measure iron, which has also the problem that it can get into the dust grain, and you are not completely sure. So you measure also some other element like magnesium to try to see how much may be in the dust and do all of this. And so here is the big concern, indeed, when we compare this metallicity from absorption to the one from emission. From emission, yes, there is some uncertainties, but we can have different elements and we can check. In stars, we can make some checks. But this is a big mess, is mostly when you put emission and absorption together. So the big progress, and we start to be able to do it, would be to be able to measure emission abundances in the same galaxy where you see absorption lines and you have absorption, and then in this one calibrate how much we actually are measuring metallicity. So that's a big limitation, but this is what we can do, I guess.
Other questions? Nobody?
Everyone is hungry.
Mm-hmm.
Food.
Everything is clear for you.
Well, that's okay, because then they will make the demonstration for next time, and we will see that everything was indeed clear.
Okay. Then if no questions, just thank the speaker again.
Thank you.